everybody, it's really nice to see you. I work at the University of Roehampton, training the next generation of outstanding teachers. They let me out to do other interesting things too, such as coming here this morning. I was part of the panel who drafted the English computing curriculum. I sit on Computing at Schools board and the board of CSTA and things like that. Really interested in having a chat with you later on today about how computing's going in your schools. I'd love to hear more. We're kind of getting to the point now. What is it, 5 years ago? 5 years ago yesterday, the expert panel, I say expert in inverted commas, submitted advice to ministers on what should be in the computing curriculum. And pretty much this weekend, they then sent it back and said, oh, we don't like that bit, we don't like that bit, we don't like that bit. Put some more maths in. So lots of binary, lots of Boolean logic went in there at that point. 5 years on, I think we're starting to get to a point where we can say, okay, this looks like effective practice in our context. This is the sort of practice which may not be terribly effective. Other subjects have had that sort of body of knowledge for a very long time now. We kind of know what works in maths education. We know what works in science education. We're still pretty much figuring out for ourselves what probably works when it comes to computing education. So this is, in some ways, a personal perspective. I'm drawing on the research evidence where we have it, but there isn't nearly as much research evidence as there are in other longer established domains. So before we get into what probably works, a few things which probably don't work, in all honesty. So we have, back in the 1980s, back in the 1970s, Papert arguing that children who'd learnt to program started looking at the world differently. He began to see how children who'd learned to program computers could use very concrete models to think about thinking, to learn about learning, and in doing so enhance their powers as psychologists and epistemologists. It's a wonderful book. I'm really inspired by what Papert writes. But Papert never did the control trial study. He never gave them a test of psychology at the beginning and a test of psychology at the end and saw if they had improved. And a number of us are starting to have our doubts now about whether learning to program a computer automatically transfers into other domains. We can help children make that transfer, don't get me wrong. We can also help them to apply their coding skills in other domains. But just expecting children to suddenly see the world differently through that experience of programming may be a little naive. Last year, or a couple of years ago now, was the study. NFER did a study of how Code Club was going. Who's running a Code Club in their schools? How's it going? I'm glad to hear it. It's a wonderful thing to do. Those of you who didn't put your hand up, go and have a look at Code Club and start running Code Clubs in your school. Now running from 9 to 13. It's really nice that they've expanded into secondary. Anyhow, the evaluation of Code Club. We got children to sign up for Code Clubs. We put them into two groups, those who could go to a Code Club that year and those who'd have to wait another year before they got their participation in Code Club. Gave them a test of coding, gave them a test of computational thinking at the start of the year. Code Club runs for the whole year. They do the full breadth of the Code Club curriculum, and then we test computational thinking and test coding at the end of the year. Going to Code Club for a year, they got demonstrably better at coding. It worked in at least that sense. They were better programmers at the end of the year than the group who hadn't. They had also improved on a test of computational thinking, but they hadn't got any better at computational thinking than the other group who didn't go to Code Club. Both groups made progress in computational thinking. There wasn't a significant difference between the two. So Code Club helps with coding, but it didn't automatically transfer into some sort of more general problem-solving skills. Mark Gusdile, writing a really good book, Learner-Centered Design in Computing Education, says that all the time since Jeanette Wing was saying computational thinking is what we should be doing, it's about looking at problems, it's about thinking about the things differently, says nobody's managed to demonstrate that these coding skills transfer across. Learn to program a computer, really good for programming computers, but doesn't make you better at making jam sandwiches. Doesn't make you better at tiling your bathroom floor. These are very domain-specific skills, it seems. The other thing which may not work is just sitting children in front of Scratch and expecting them to learn things. Scratch is tremendously accessible, huge advocates for Scratch. I love Scratch. But you've got to get in and teach this. You can't just expect children to figure out the whole of Scratch for themselves. There are teachable things in there. Mitch Resnick, the guy behind Scratch, tells the story of the child who was making their game in Scratch and wanted to have a thing which was keeping track of the score. Her approach to that is to create a score costume or a score sprite with lots and lots of different costumes. So it goes from 0 and then shows a 1 and then shows a 2 and then shows a 3, and using the little change costume block to move through those scores. Somebody had to come in and teach the girl what a variable was, and whoa, the lightning strikes, the light bulb moment when she suddenly sees that, oh yeah, there's something to do that built into Scratch. She wouldn't discover that for themselves. So a couple of Dutch researchers analysed 250,000 Scratch projects. I assume they got a computer to help them do that job, and found that in many of those there were these things like smelly code, that children had made fairly fundamental mistakes or learning opportunities in their Scratch code. They'd not learned things because nobody had bothered to teach them these things. Another one which may not work in my view, other people may disagree, is this notion of unplugged computing. Dijkstra argues you don't need a computer in order to do any computer science, just as you don't need a telescope to do any astronomy, although how much astronomy would there be without telescopes? So we do the what's your recipe for making a pizza? I think a couple of years ago we may well have gone around the room and talked about our recipes of making pizza if you were here then, and that's fabulous, and you're learning something about algorithms. But that's not the same as actually writing code on a computer, and nobody actually, well, okay, if you're making a production line for pizzas, you might need to actually write the program to make pizzas, but there's a separation there. And so when they've looked at these CS Unplugged activities, they've seen that actually, yes, they do help construct the ideas, they do help pass on the idea of what an algorithm is, and that's great. But actually it seems to really turn children off computing if all they do is recipes for jam sandwiches and pizzas and other unplugged activities. They don't seem to enjoy the subject nearly as much as when there are actual computers involved. So what am I saying here? Yes, teach the programming. Use the programming to teach the computational thinking, but these are teachable things. This is our responsibility as educators. One final thing that probably doesn't work, personal bugbear this, flowcharts. Of course we want children planning what they're going to code, but actually drawing a flowchart doesn't seem to be at all productive. Real coders do not use flowcharts. Any real coders in the room? Do you use flowcharts, sir? There you go. Okay, so n equals what? 100% of those who I asked. Okay. We put it onto exam specifications because it's easier to test a flowchart. But actually it doesn't seem to make any significant difference to how well people get on with coding. So that's the things which we probably shouldn't be doing quite so much. What does seem to work? Well, being honest about computational thinking. Sorry, here's the list of 10 things. I'll try and put this back on the end if you want to come and ask questions about those. So being honest about computational thinking. When Wing coined the term, she was talking about the thought processes involved in coming up with a solution to a problem so that a computer could implement it. If we separate out the coding from the computational thinking, if we remove the computation from computational thinking, it just becomes thinking. It should come before the making the machine do the work for you. Yes, you can lay the foundations of it without using computers, but really it comes into its own when we're using a computer as an end part of the process. Tedder and Denning, really influential paper published a year ago, computational thinking offers powerful tools for people who design computations. We don't need to make exaggerated claims about it will solve the world's problems, that it will transfer across into maths, into English, into every other subject, because of how important it is to be able to use a computer well. Think of any sphere of academic inquiry or employment where computers aren't going to be important. In those, computational thinking probably doesn't work, doesn't help. But in the ones where computers will play a role, which is, by the way, pretty much all of them, then computational thinking helps, because computational thinking is about designing computation. In order to get the problem solving, the thing that didn't work in the Code Club evaluation, to get that computational thinking gain as well, we have to step in and teach this. Back in 1983, Roy P. did do the control trial study. Put the class into two groups. Half of the groups he taught Logo programming, let them program in Logo, did the test at the end. Had the Logo group got any better at planning skills, as he called it back then, than the other group? No, they hadn't. But if you teach the planning skills, if you teach the computational thinking skills, then that does seem to work. How might you go about doing this? One approach is this idea of subgoal labeling, of actually before you start doing the code, what are the steps? This isn't the same as a flowchart. This is thinking about how to solve the problem and writing that down. It's commenting the code first. It's putting the little comment blocks into Scratch first. Have we got time? We've just about got time. Okay, how would you go about this? Talk to your neighbour. If I give you a list of numbers, one at a time. When I say minus 999, you stop. How would you calculate, or get a computer to calculate, the average of those numbers up to, but not including that point? Talk to the person sat next to you. Please. Okay, has anybody got a solution or an outline of a solution that they're willing to share? Anybody got a method? Oh, I almost saw a hand go up. No? Anybody? Oh, all right, here we go. This is pretty much what you have to do. Okay, here are my sub-goals. I have to clear some memory. I have to sort of keep track of things here. I'm going to go loop through the data, one item at a time. I'm going to test if it's minus 999. If it is, then I've got to skip out. If it isn't, then I've got to update the variables. What variables do I need to keep track of? What things do I have to keep track of to do this? The number of the numbers, yeah, how many things? And total so far, yeah. So here are the 2 bits of memory I've got to use. Keep track of the total so far, keep track of the number of things I've got, yeah? So I've got to initialize those and update those one at a time, and then at the end, we display the result. Here, so once you've got those steps there, once you understand the structure of the code, then the rest is fairly mechanical. Here's the program in Python to do it. You could do this in Scratch, but the text is reasonably clear. So my initialized variable subgoal, I set total to 0, I set count to 0, I loop through the data, or until we hit the end, then we input a number. If it's minus 999, then I skip out. Otherwise, I increase the total. Otherwise, I increase the count by 1. Once I've skipped out of that loop, in other words, hit minus 999, I simply divide the total by the number. Yeah, I hope you got something not that different to that yourselves. Yeah? Should work. Is there a problem with this? Everybody happy with the code? One slight problem. What if there's no numbers in the list? What if you type in minus 999 on the first go? I'll leave that as an exercise for you. But the idea of scaffolding the construction of the program, much, much better, demonstrably better than just saying, write the program. What are the steps that we go through there? Another thing we're trying to do is develop a child's understanding of what a computer is. Sorver in his paper talks about the notional machine. The child has some sort of mental model of what a computer is, what a computer does. My daughter at the age of 6 months knew that if she closed the laptop lid, then Mummy and Daddy would start paying more attention to her than otherwise. She knows that if she strokes the tablet screen, then it will respond to her in some way. I think at that age, she has some concept of input, process, output. When you run that code, I've not executed that program, but if you step through that in your head, can you predict what it will do? What's your model of how a computer works? One of our jobs as computing educators is to give them a better model of how a machine works. One way we do that is through stepping through the code in our mind, of having this mental construct of what a computer is. When we're teaching children to read and write, we do the reading first. They listen to stories. They read stories before they start writing their own stories. Why should it be any different in computing? Shouldn't they be familiar with what a program does, what a program looks like before they start writing one of their own? One of the reasons why we have that problem with my 250,000 Scratch projects is because children don't look at Scratch projects before they start writing their own. Show them a good example, what a good one looks like. We do that over in English teaching. Shouldn't we do a bit of that in computing teaching? And being able to think logically. We built reasoning about code into the curriculum. So use logical reasoning to predict the behavior of simple problems with 5 to 7-year-olds. Here is a simple program. What will it do when I click the green flag? When we press the go button on the b-bot? What will this code do? Is part and parcel. And why will it do that? That's the logical reasoning. Key stage 2, use logical reasoning to explain how an algorithm works and to detect and correct errors. Everybody spotted my -999 problem. Key stage 3, similar sort of thing going on. Evaluate computational abstractions. You don't have to make computational abstraction, although we think it's best if you do. But what does this computational abstraction do? Is it a good model for how things work? And of course, using logical reasoning to compare algorithms for the same problem. So here you go, here's some code. This is written in Logo, which is an old language now. This is the language Papert developed. So don't type it in, but tell me what this code would do. Run it on the machine in your head, the Notional machine. I love it when people wave fingers or move hands around. You're absolutely right. Yes. Okay. Anybody want to describe it? Circle of squares. Thank you very much. Is that what you've got? Is that the picture in your mind? Here we go. So it draws a square, it turns right, it draws another square, it turns right. You're looking really confused, sir. Okay, right. Let's debug the Notional machine there. Okay. Well, the middle bit of the loop, repeat 4, forward 100, right 90, draws me 1 square. I'm going to draw 10 squares, each turn round through 36 degrees. Where did I get the 36 one? Well, 10 36s make my 360. Getting children to work collaboratively. This is proven development methodology out in industry. You get 2 programmers sharing a screen, sharing a keyboard, sharing a mouse, not because they can't afford enough computers to go round, but because getting 2 brains to work together on the same problem is much more efficient, much more effective, much more reliable than just having lone coders working on the problem and then trying to join their code together. Of course, you don't want to do that in the NEA, do you, Tig? No, generally discouraged in the non-exam assessment. They've got the data on this, they did the studies, and found not only did they get better code, but they also enjoyed computing and were much more motivated to carry on studying computing more if they did that pair programming as part of the approach to teaching. It also really helped the lower achieving students. So you look at their, as they call them in the States, their SAT scores, SAT scores, on entry to the school. You look at how well they did in the computing exams or the computing practicals. And of course, those who, high ability students at the start of the course did better. But once you move to pair programming, then it really did help the lower achieving or the lower prior attainment students to achieve as well as they possibly could. So we do this at Roehampton. We get our students working with a partner to produce a game in Scratch based on a children's book. Do this with your pupils. Get them programming in pairs, not during the NEA, of course, but also get them answering questions in pairs. Again, proven approach in higher education over in the States, this idea of pair instruction. We put the question on the board, but we don't get them to vote straight away. We get them to talk to their friend about how they should vote, and then 2 talking together. It's not about assessment. It's about them teaching one another, explaining the idea to one another, and then put it back at the end. And again, the data that does actually seem to work. One of the projects we've been working on over the last year and a half is this Project Quantum, about where you get these questions from. We have out there on the website now, what is it? It's like 6,000 plus crowdsourced multiple choice questions for testing computing, most of them around sort of Key Stage 3 GCSE level, but an increasing number of primary ones on there as well. All for free, all for you to use however you want. Use them as a test if you want, but better still, use them during your lessons to get children to think about what the answer should be to this. Over in the States again, and indeed here, when it comes to undergraduate CS education, there's this real problem of some people do very, very well, and some people really struggle. What makes that difference? And it seems that the key difference is their attitude to this. That those who approach their mistakes with a positive attitude, those who are willing to learn from their errors, willing to debug their own code, those who believe that they will get there if they work hard enough and if their lecturer, teacher explains it well enough to them, tend to be the ones who achieve best. The thing that seems to matter is their attitude to the study rather than any particular prior knowledge. There's this myth that there's a two-hump distribution, an M-shaped distribution to computer science. You have some students who are going to be really good at this and some who are going to really struggle with this. And, the ones who are going to be really good at this, somehow they've got the geek gene or they're naturally talented at this. It's nonsense. When you actually look at the distribution of grades, we get this with GCSE, we get this with A-level, you get this with 94.2% of undergraduate CS courses. It's a perfectly normal distribution. Loads of people in the middle, some at the top end, some at the bottom end. There's nothing special about coding when it comes to that. What does seem to matter is the mindset. And okay, you've sat in other rooms and people have talked to you about growth mindset. But Quintin Cutts did the study. This is undergraduates at Glasgow University. 2 groups, proper randomized control trial stuff. Both groups he taught about computer science. He taught them how to program. One group he also taught them about growth mindset, about how their attitude to their study, having a positive attitude when they make mistakes, believing that they will get there if they work hard, and all of that, the Carol Dweck stuff. He taught them about that. Guess which group did best in the end of year exam? It was the growth mindset half, by a significant difference. Teaching them the importance of their attitude seems to be significant. The other thing which we can't really do much about is, surprisingly enough, prior experience really does help, particularly when it comes to undergraduate CS education. Those who've programmed before will do better in the exams than those who are new to programming when they start the undergraduate computer science degree. You kind of wonder how they chose to study computer science at university, but that's for another time. Okay. So what can we do about that? Well, starting early. If you're worried about GCSE computer science grades, then this kind of explains it. The group who did, we know that computer science gets lower grades. So if you look at the same student doing both physics and computer science at GCSE, typically it's about 3/4 of a grade better in physics, and physics is by no means a walkover subject when it comes to GCSE. So there is a difference in that, even when it's the same student. What explains that? Well, it could be that they don't work hard enough, could be that their teacher isn't teaching well enough, could be that the exam actually is harder. But really what's going on is they've not done enough computing before they start the course. The cohort who did the GCSE last summer had 1 year of national curriculum computing before they started their GCSE course. When it came to physics, they'd done 9 years of some sort of physics in school. They played with trolleys, they played with cars, they played with springs and lit up bulbs and made lighthouses when they were in primary school. If you only compare 1 year of prior experience to 9 years of prior experience, don't be surprised that there's 3/4 of a grade difference. So in terms of what we can do about this, start early and make sure the foundations are really firm. Who here is working in early years? Yay! Okay, lay the foundations of computational thinking. Get them solving big problems. Get them, exploring strategies, changing their approaches to do things. Doesn't have to use a computer at that point. Go for that characteristics of effective learning ideas, please. Then give them a couple of years playing with Scratch Junior or playing with the blue bots. Make sure they've got a really clear idea of how an algorithm gets turned into a program. And then 4 years of Scratch, well, I suppose, or something similar, but really just Scratch, in primary education, up in Key Stage 2, so they can all code their drill and practice game, code upon game, pretty much independently by the time they move on to secondary school. And then if you lay a firm foundation of 3 years of text-based programming, getting to the point they can write bubble sort in Python by the end of year 9. I'm pretty confident that if we can do that for everybody, those who go on to study GCSE computing will do pretty well, will do at least as well as they do in physics. If we can lay that foundation first, we'll be all right. So here, what tools do you use? Start with the Bbot. Have the Bbot, convert the program into code. Move on to Scratch. Don't worry if it's Scratch again. There's so much you can do with Scratch. There really is. If you can do sequence selection, repetition, work with input, output, and variables, there is no computational problem that you cannot solve. There may be other more appropriate languages, but if you can tick off those 6 things which you can do in Scratch, all computer problems become soluble. Python, lovely first text-based teaching language, And if you get those right, then you can get to Haskell by the end of year 13, I'm sure. Good luck with that, Tig. Okay, don't rush into text. The blocks really do help. While the interface did not seem to affect users' attitudes or perceived difficulty, they can code the same thing in text or in blocks. The students who were using the block-based interface were willing to stick at the task more. They focused on the task and they moved on to more and more of the goals. Rushing through to text is probably not such a good idea. You can do amazing things with blocks. If you're interested in implementing a recursive version of quicksort, you can do it in a block-based programming language. You do not need Haskell or Python in order to do really sophisticated computational thinking, computer science stuff. There's the evidence, again, from study in the States. So block-based language, they stick at it for longer and generally do more of the exercise than when it comes to text. Why is that? Because when you're programming, your poor old brain, if you're using a text-based language, is having to do two things at the same time. It's having to think about how to solve the problem, the semantics here, what's my solution going to be, and then translate that into this rather weird syntax of whatever the programming language happens to be, where the colons go, where the spaces have to go, or tabs to indent the lines. Trying to do both at the same time is asking for trouble. Make sure that they understand how to solve the problem, then translate that into text. Thank you very, very much. Do you want to do questions now? Time for questions now?